Hello and welcome to my science tutorials. In today's video, we are going to be talking about the reactions of alkenes. Before we begin, if you are new to my science tutorials, kindly consider subscribing and pressing that notification button so that you don't miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So let's begin. So hydrohalogenation. Now the hydrohalogenation is just adding what? HX to an alkane. Alright, so like the name suggests, this reaction involves the reaction of a hydrogen halide, which is of the form HX, and examples are what? Hydrogen bromide, HCl, HI, and other examples, okay, to an alkene. So when we add a hydrogen halide to an alkene, we call the reaction hydrohalogenation. Okay, so let's have a look at an example and have a feel of how this reaction looks like. So assuming we have the alkene CH3 bonded to another CH3, then we have doubly bonded to what? Another carbon bearing hydrogen, and then CH3. Then we are adding what? HBr to this. Now, under normal circumstances, this bond is going to break, and then the hydrogen will be attached to one of these carbon, and then the bromine will be attached to another carbon. So there are two likely products that are supposed to be formed. So we can have our CH3 attached to carbon CH3 here. Then we have our bromine attached over here. Then we have our second carbon with the hydrogen. Then we have the CH3. Then we have the hydrogen over here. Okay, so this is the bromine being added, and then this is the hydrogen to being added. Or we can have the CH3 attached to the carbon bearing the other CH3. Then we have the hydrogen attached over here. Then we have the other ones over here, so CH3, and then we have our bromine over here. So these are the two likely products that are formed when we have hydrohalogenation. Now from experiment, it is observed that what? Only this product here is the only product formed, and this is not formed. So why is it that only this product is formed? Okay, it turns out that the hydrohalogenation reaction is what? Regioselective. By regioselective, we mean what? The position where the hydrogen is going to attach itself to one of these carbons is determined by the reaction, and then the position where the bromine is also going to attach is also determined. So the regiochemistry or the regioselectivity of this reaction follows the Markovnikov addition. That is to say, the hydrogen attaches itself to the carbon bearing what? Or the carbon that is less substituted. If we look at these carbons, we have carbon 1, carbon 2. Let me use another color for this illustration. Let me use green. So we have carbon 1 and then carbon 2. We can see that carbon 1 has what? 2 alkyl groups, 1 and 2. Then carbon 2 has only 1 alkyl groups. So in terms of what? The number of alkyl groups that carbon 1 and carbon 2 has, carbon 1 has more alkyl groups, and hence it is what? More substituted. So when this reaction occurs, the bromine will be attached to what? The most substituted carbon, and then the hydrogen will be attached to the less substituted what? Carbon. And if that happens, we can see that this is the only product that will be formed. Now let's look at the mechanism of this reaction to appreciate what actually happens when this reaction is occurring. Okay, so let's have our CH3, C bonded to another CH3. Then we have the double bond CH, then CH3. And then we are adding our hydrogen bromide to it. Now in the first step of this reaction, we have the protonation of the double bond to form a more stable carbocation. So like I said, the double bond over here is an electron rich center, and then this is what? This bond the hydrogen over here has a partial positive charge, and then the bromine has a partial negative charge. So the double bond over here has an electron, so it will be attracted towards the positive charge. So the hydrogen will attack, the double bond will attack the hydrogen, okay, and then breaking the electrons onto the bromine. So we have this CH3 here, then we have this carbon, then we have our CH3 at the top, then this double bond becomes a single bond, then we have CH, the H over here, then we have the other CH3 attached. Now where does this hydrogen goes? Okay, like I said, this reaction is reduced selective. That means what? It follows the Markovnikov addition. So by Markovnikov, it means the hydrogen will go to the less substituted carbon, then, and the less substituted carbon between these two carbons is this carbon over here, because it has what? There's one alkyl group attached to it. So the new hydrogen that we are adding is what we have over here. So let me use a box to cycle it, okay? And then when that happens, because this alkene, this carbon over here, is now having 3 bonds, it will now assume what? A positive charge, okay? Now that it has assumed a positive charge, this is called what? A carbocation. So this is a carbocation. Now let's look at something. We can see that this carbocation, the carbon over here bearing the positive charge, is attached to what? 3 other carbons around this. So this is what? A tertiary carbocation. Okay, so now that we have the tertiary carbocation being formed, we still have the bromine anion in solution. So it will now attach itself, it will now attack the carbon bearing the positive charge, and then we get our product, which is what? CH3, C, CH3, then we have our bromine here, then we have CH, then CH3, then our hydrogen over here. So this is our product. Okay, now someone will say, what happens if the hydrogen is attached to the more substituted carbon? Now let's look at what happens if that happens. So let me use another color. Okay, so in case the hydrogen goes the other way around, okay, so we are going to have this, then we have our carbon attached to CH3, then our hydrogen will be attached to the more substituted carbon. Note, this reaction is not feasible, okay? Not feasible, which means it does not happen, but just for demonstration's sake, I'm going to do it. Okay, so we have our carbocation being formed on this carbon, and then we have our Br minus in solution. Okay, so we can see that when the double bond attacks the proton, the hydrogen is now attached to the more substituted carbon, which is not supposed to happen. But in case this happens, let's look at something. This carbon over here is attached to 2 other carbons, so this is what? A secondary carbocation. Now in terms of stability, tertiary carbocation is stronger than what, or is more stable than what? Secondary carbocation, which is more stable than what? A primary carbocation. So if this happens, to achieve stability, this carbocation over here will undergo something that we call rearrangement reaction. Now we will be talking about rearrangement reaction in other videos, but just so you know, the hydrogen over here will have to move to this side, and then the positive charge will now come on this carbon, and that is the rearrangement that we are talking about. And if that happens, we call it what? The hydride shift. Hydride shift. Okay, so that is, we are changing the position of hydrogen to achieve what? A more stable carbocation. So if that happens, we have our CH3 attached to the carbon over here, then we have our CH3, okay, then we have a positive charge over here, then we have C, hydrogen, then the new hydrogen that has moved here is this one over here, then we have our CH3 again. So if we look at this, we are looking at what? A tertiary carbocation over here, because this carbon is attached to 1, 2, and 3. So which is equal to what? This. Okay, so we can see that even if this pathway happens, there will be a rearrangement reaction which will still form what? A tertiary carbocation, and hence this will be the product that will be formed at the end. Okay, so even though the addition doesn't go this way, in case it is an experiment, so in case it happens, the reaction undergoes rearrangement to achieve stability, and then we form just our product. All right, so let's look at more examples to understand what we are actually doing. So let's look at this. So we have CH3 bonded to what? This. By the way, this is propene, and then we are reacting it with what? HBr. Okay, so from directly we know what the Br or the bromine will be attached to the more substituted carbon, which is what? This carbon over here. So the product that we are going to get, without even writing the mechanism, is going to be something like this. Our Br will be attached over here, then we have hydrogen, hydrogen, hydrogen over here. So this is going to be the only product that is formed. Now let's look at the mechanism. So this is how it happens. So we have our CH3 bonded to our carbon bearing the double bond, and then we have the two hydrogens over here. So we have our HBr over here. So this is what? Partially positive, partially negative. So the double bond over here will attack the proton, then expelling the electrons over here onto the bromine. So we have our carbon-carbon single bond, then we have what? Our CH3 over here, and our hydrogen over here. Now this hydrogen, because this reaction goes by a Markovnikov addition, the hydrogen will attack the less substituted carbon, which means this carbon, because it has what? Two hydrogens. So we are going to have that hydrogen, this one, coming over here and then leaving what? A positive charge on this carbon. Now if that happens, we can see that this carbon is attached to what? Two other carbons. So this is what? A secondary carbocation. Secondary carbocation. Okay, now we have Br minus in solution, so it will then attack the carbocation, and then we get our product over here, CH3. Then we have the hydrogen, and then we have the bromine here, then attached to what? Another CH3. Now let's see what happens if the reaction were to go the other way around, which is not even possible. So this is the sole product. So this is our sole product. Okay, but if the hydrogen were to be attached to this carbon, let me use red to indicate that reaction just for demonstration sake. So this is not possible. Let me put, so this not possible. It means it's not going to happen, but let's just do it for demonstration sake. So if the double bond attacks the hydrogen, and then the hydrogen goes to be attached to the more substituted carbon, we are going to get carbon with the hydrogen here, then we have CH3, then single bond this H and H. So the positive charge will not be here. Now we can see that this carbon is only attached to one carbon, so it is what? A primary carbocation, which is not stable. Like I said, a tertiary carbocation is more stable than secondary, and is more stable than what? A primary carbocation. In this reaction, the most stable carbocation that can be formed is secondary carbocation. So even if the primary carbocation is formed, it is going to undergo what? Rearrangements to form what? The secondary carbocation, and then this will be the sole product that is formed. Okay, let's have a look at more examples. So let's use a cycloalkane for this demonstration. So we have this with what? CH3 here, then hydrogen here, and then we are adding what? HBr to it. So from here we know very well that we are going to get a product that looks like this. Then the double bond will go, and we still have our CH3, then the bromine will come over here, and then we have our hydrogen here as the product that is formed. So let's look at the mechanism. So by now we are all comfortable with how this reaction goes. That is, it goes via what? The Markovnikov addition. So we know our HBr this is what partially positive, this is partially negative. So the double bond will attack the proton, expelling the electrons onto the bromine. So we have over here, so we no longer have the double bond. Then we have our CH3 here, and then we know that the hydrogen will go to the less substituted carbon. So between this carbon and this carbon has what, one carbon here, and then another carbon. So it has 3 carbon attached to it, but the carbon over here has only what, 1 carbon, 2 carbons attached to it. So this is the less substituted carbon. So the hydrogen will attack over here. So we have here and here. So our carbocation is formed over here. Now if the carbocation is formed over here, it means this is carbon 1, carbon 2, carbon 3. So this is what, a tertiary carbocation. It is very stable. So we have our Br minus, which will now what, attack the positive center of the carbocation to form our product. So we have CH3 here, the Br over here, and then we have the hydrogens over here. Okay, so let's have a look at one final example, and then we can end the tutorial. So we have CH3, C, CH3, doubly bonded to CH, then CH2, CH3. Then we are adding what, HCl to it. So what is going to be our product? So straight ahead, we know that this is carbon 1, this is carbon 2. So the carbons bearing the double bond. And if you look at carbon 1, it has what, 1, 2, and then 3 carbons around it. Okay, but then this carbon has hydrogen and then 1 carbon attached to it. Okay, so it means this carbon 1, is our most substituted carbon. So it means our what, chlorine will attack this carbon. So we have CH3, C, CH3 at the top. Then we have our chlorine attacking this carbon. Then we have C, H. Then we have the CH2, CH3 here. Then we have our hydrogen coming over here. So let's write the mechanism for this. So if we have our compound over here, CH3, doubly bonded to C, H, CH2, CH3, our HCl will come in this form. This is what, partially negative, what, partially positive. So the double bond will attack the proton, expelling the electrons onto the chlorine. So we form our what, carbocation. So we have CH3C, CH3, single bond C, H, CH2, CH3. Because this carbon is the less substituted carbon, the hydrogen will attach itself over here, and then we have the carbocation over here. By the way, this is a tertiary carbocation. So we have the Cl minus still in solution. It will now attack the carbocation to form the product that we have over here. So we have CH3 attached to the carbon CH3, then we have the chlorine over here, then C, hydrogen, hydrogen, then we have CH2, CH3. So this is how we do the what, the hydrohalogenation of alkanes. And then one thing we need to know is that this reaction, in terms of what, regiochemistry, that is the point of attachment of the species, goes via what, Markovnikov addition, Markovnikovs addition. That is, the hydrogen goes to the less substituted carbon. And in terms of what, stereochemistry, it doesn't show any stereochemistry. That is, you can add the bromine or the hydrogen to either side of it, either both syn or anti, it is still the same. So the free radical addition of hydrogen bromide to an alkane is one of the reactions of alkane. Now let's have a look at this general equation. So if we have an alkane, the general form of an alkane, then we add hydrogen bromide to it. Normally the product that we get is what, the bromine over here is being attached to what, the more substituted carbon. So assuming in this case this is our more substituted carbon, let me use asterisk over here. If this is the case, so it means our bromine over here, upon reacting with what, this alkane, the bromine will be attached to the more substituted carbon, which I'm using as this. So we are going to have this, then with the bromine attached to it, then the hydrogen over here will be attached to the less substituted carbon, and then we have our product, this as our product. So this reaction is what we call the hydrohalogenation. The hydrohalogenation of what? Of an alkane, and it goes via what? The Markovnikovs addition. Markovnikovs addition. Okay, but now what if we want the bromine? Okay, if we want the bromine, okay, on the less substituted carbon, okay, that is in this example, if we want the bromine to be what? On this carbon rather than this carbon, what do we do? This is where the free radical addition of what? Hydrogen bromide comes into place. So for this reaction, if you want it to go via the anti-Markovnikovs addition, all we need to do is to add what? A peroxide, okay, to this reaction. Once we add a peroxide to this reaction, it does not go via the Markovnikovs addition again, it goes via the anti-Markovnikovs addition. That is, if we still have our alkane, and then we add what? Hydrogen bromide in the presence of what? A peroxide. Okay, once we add a peroxide to it, we get what? The anti-Markovnikovs product. That is, we add the hydrogen to the more substituted carbon, and then we add the bromine to the less substituted carbon. So let's have a look at how this reaction goes. So like I said, the general alkene formula is this, and then we are adding what? Hydrogen bromide in the presence of what? A peroxide, which we are saying is this. So if this with the asterisk, this carbon is our more substituted carbon, it means if we react this, we are going to get the hydrogen being attached to the more substituted carbon, and then the bromine being attached to the what? To the less substituted carbon. So let's look at the mechanism for this reaction. So the first step that we call the initiation stage, or the initiation step, is the what? Is the formation of what? The radical, okay, or the alkoxy radical. What do we mean by this? So the peroxide that we have over here, okay, would decay or would dissociate in the presence of heat to produce alkoxy radicals. Okay, so it means this peroxide over here will undergo what? Homolytic cleavage. Will undergo what? Homolytic cleavage to produce what? Alkoxy radicals. So it will produce this, then with one electron from the bond over here, then another one, okay, with one electron. Okay, so this is what we get, and so this is what we call the alkoxyl radical. Now once the alkoxy radical is produced, one of these radicals will now react with what? Hydrogen bromide. Okay, so during the reaction, okay, this we have one electron here, then we have two electrons over here. So one of the electrons will react with this, and then breaking the other electron onto the bromine over here. So from here we get what? The O now forms a bond with the hydrogen, then we have what? The bromine radical being produced in solution. Now once we have the bromine radical being produced in solution, it will now go and then attack the alkane that we have. So we have our alkane here, then plus the bromine radical. Okay, mind you, we are saying this carbon is the most substituted carbon, and because we have what? A peroxide in this reaction, the bromine will what? Will attack. This will happen. One of the electrons from the double bond, okay, will react with the one electron over here of the radical, will react to form a bond. Now that bond will be situated on the what? On the less substituted carbon, which is this one that we have over here. So we have this single bond, then we have this, and then Br. Okay, so if this happens, it means the second electron from this bond will now be placed on the most substituted carbon. So we have the most substituted carbon, which is this carbon here, becoming a radical. Okay, once we have this radical, okay, because this carbon is the most substituted carbon and the radical is on it, it is now very, very stable, and hence the reaction can continue. So another hydrogen bromide will now come. So from here, this radical will also react with the 8Br. Mind you, I'm using half arrow, which means what? One electron from here, one electron from here to form a bond. So this one also breaks onto this. So once the HBr now reacts with this radical, we now have this with the hydrogen attached to our most substituted carbon, and then we have the bromine attached to the less substituted carbon, and then we have the bromine radical over here, this in solution, plus this radical in solution. Now this is now our product. This we have over here is our product, but we can see that we have another bromine radical in solution. So because we still have another bromine radical in solution, this reaction is described as what? As a chain reaction. That is, even upon getting the product, if we still have the bromine radical will still be produced. So in the presence of what? Excess alkene, this bromine radical will now attack another alkene molecule to produce the product, and then yielding another bromine radical, and then it goes on and on and on until we get what? More product, or until we no longer have any alkene for the reaction to further continue. All right, so let's have a look at an example to actually appreciate what we are doing. So the first example we want to look at is the free radical addition of what? HBr to what? To propene in the presence of what? In the presence of what? A peroxide. Okay, so let's have a look at that. So if we are having a propene is of the form, have this is propene, H, then we have hydrogen, then we have CH3. Propene means it has 3 carbons, so we have 1, 2, 3, and then we have the double bond in between them. So this is propene, and then we are adding what? HBr, hydrogen bromide, to it in the presence of what? A peroxide. So straightforward, we know this reaction will go via what? The anti-Markovnikovs addition, because of the presence of the peroxide. The bromine radical will attack the less substituted carbon, and then we have our product over there. So straight from here we can see that we are going to get this as our product, CH3. Then the hydrogen will come to this, is the most substituted carbon, so the hydrogen will come here. Then we have this, and then our bromine will now be attached to the less substituted carbon, plus another bromine radical in solution. Okay, so let's write the mechanism for this. So the mechanism is straight ahead. Before even the reaction occurs, the peroxide has to what? Dissociate in the presence of what? The presence of heat. So this is what goes on. We have heat over here, so this will undergo homolytic cleavage to produce what? 2 alkoxy radicals, which looks like this. So this is what we are calling the alkoxyl radical. Now once the alkoxy radicals have been produced, we have the alkoxy radicals, okay, one of them reacting with what? Hydrogen bromide. Okay, so one of these will form a bond with the hydrogen using 1 electron, breaking the other electron onto the bromine. So we have this produced, okay, then plus the bromine radical. Okay, so this is the electron that is obtained from the breakage or the cleavage of this bond. Now once we have this radical, bromine radical, will now come and attack the propene for us to get our product. So let me do that on a new page. So we have our propene, CH3, doubly bonded to another CH, then H. So we have our what? Br radical. So this bond will come, then this will also attack to form our what? Our radical intermediate. Now because this carbon is the less substituted carbon, it means the bromine will be attached to this carbon. So the other electron that is within this bond will be what? Will not be attracted to the most substituted carbon. So we are going to have this. Then we have our CH3. Then we have the radical on the most substituted carbon over here. Then we have single bond. Then we have the H over here, hydrogen here, hydrogen here. Then we have our bromine over here. Okay, so once we have this, we can see that this radical is the carbon over here is attached to two other carbons. So it is what? More stable than if the radical were to be here, which would just be attached to what? One carbon. So this radical is more stable than what? If we have the radical over here. So from here, another HBr in solution will now react with this radical. So one electron from here will now react with this electron, breaking the other electron onto the bromine, and then we now get our product, which is in the form CH3 carbon, hydrogen. Then we have the hydrogen over here. Then we have CH with the bromine plus another bromine what? Radical in solution. Okay, so this is the product that we get. And then this bromine radical, if there are excess what? Alkane molecule in the solution, this bromine radical will go and react with the propene again to produce this product again, and then the reaction continues. Okay, but this is our product, and then it is what? An anti-Markovnikovs addition. Anti-Markovnikovs addition. That is what? We are adding the bromine to the less substituted carbon. Okay, also before we continue, we need to note something. This reaction, let me use another color to demonstrate that. This reaction is only possible if we add what? An alkane. If we add an alkane to what? Hydrogen bromide in the presence of what? A peroxide, to get what? Our anti-Markovnikovs product. Which means if we add another hydrogen halide such as what? HCl or hydrogen iodide, this reaction does not occur, or we don't have the anti-Markovnikovs addition. Why is it so? This is because what? The reaction of what? HCl and then hydrogen iodide do not undergo the reaction, because what? The reaction between HCl and then what? Hydrogen iodide with alkane is an endothermic reaction. So because it is an endothermic reaction, the reaction does not have the right what? Reactivity for the radical chain reaction to occur. So to note is the fact that the addition of what? Alkane with HBr, okay, because we have a peroxide over here, the peroxide brings about a new term that we call the peroxide effect. The peroxide effect. This is E. Now, the peroxide effect is simply the change in what? Reduced selectivity of addition of HBr to an alkane in the presence of a peroxide. So we can see that normally if we don't add peroxide over here to this reaction will go via the Markovnikovs addition, where the hydrogen bromide, the bromine will be added to the more substituted carbon. But because we have a peroxide over here, and due to the peroxide effect, the hydrogen bromide, the bromine is being added to what? The less substituted carbon instead of the more substituted carbon in hydrohalogenation. So let's continue with another example. So we have this alkene as the starting material, CH3, then we have double bond C, CH3 plus what? HBr in the presence of what? A peroxide. So we are being asked to write the product and then the mechanism as well. So straight ahead, because we have the peroxide over here, we know this reaction will occur via the anti-Markovnikovs addition, which means the bromine will be attached to the what? To the less substituted carbon. If we look at this starting material, we know that this carbon, okay, has only one alkyl group, and this second carbon has two alkyl groups. So therefore this carbon is the less substituted carbon. So the bromine will be attached to this carbon, so we can write our product without even thinking. So we have our bromine here, then we have CH3 at the top, CH3 here, then we have our hydrogen here, plus another bromine radical in solution. Okay, so how can we convince someone that this is actually what happens? So let's write the mechanism for this. So in the mechanism, first step, we know that the peroxide will dissociate, okay, homolytically to produce alkoxyl radicals. So we have this, okay, don't forget the 2 lone pairs that are on the oxygen. So once we have the radical, this radical, okay, will now react with hydrogen bromide, and then if this happens, one of the electrons over here will react with this electron, breaking the other electron onto the bromine. So we have this, which is technically an alcohol, plus Br radical. Okay, so this radical now goes to initiate the reaction. So we have our alkane with CH3 doubly bonded to CH3. Then we have the bromine. Let me write it somewhere here small. Radical. I will just ignore the 3 lone pair over here. So this one of the electrons over here will now attack this. Okay, so because this is the less substituted carbon, it means the bromine will go here. So the other electron will be will now come onto this carbon. So we have our CH, then we have the bromine. Let me put it here. Then the CH3. Then we have this. Then the radical will be on this carbon. Then we have CH3. Okay, so we can see that we form the radical on the most substituted or the more substituted carbon over here. So from here, another HBr will now come and attack, and then we have this occurrence. So from here, let me use another color to write the product so we can differentiate. So from here, we can see that our product will be we have the bromine over here attached to the carbon with hydrogen, then CH3, then attached to the new hydrogen will now form a bond at the top over here, which is this one. Then we have our CH3, then our CH3. So this is the product plus Br radical in solution, and then this Br radical will then go back and then react with the alkene again to form the product, and then it continues. Like I said, this reaction is a chain reaction. Now let's look at one more example and then we end this tutorial. So in this one, we are going to use a cyclic alkane. So this is our alkane, and we are adding HBr in the presence of a peroxide. This one we have been given a distinct peroxide, so we have this as our peroxide, CH3. Okay, and then we have been told to find the product of this reaction. So the moment we see an alkane, we see HBr, and we can see the peroxide, example of a peroxide given, we know straightforward this reaction will go via the Anti-Markovnikovs addition. So mechanism. First of all, we know the peroxide over here, CH3, C double bond O, 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 C double bond O, CH3, will undergo homolytic cleavage in the presence of heat. Don't forget this, in the presence of heat, to form the alkoxy radical. So in this case, we are going to have this CH3. Mind you, this will undergo the homolytic cleavage like this. So the electrons are being shared. So we have this O, then O with the radical over here. So we have 2 of this. Alright, so once we have this, oxygen always has 2 lone pairs. So once we have this, the CH3, the radical, the alkoxy radical over here, okay, will now react with with the hydrogen bromide that we have over here. So we have the HBr. So this happens, okay, breaking this one of the electrons onto the bromine. So we have CH3, C double bond O, then we have O, then H, and plus the Br minus, sorry, the bromine radical in solution. So the bromine radical from here will now attack the alkene. So we have our alkene over here plus the Br radical. Okay, let me use this. So this is our radical. Okay, now if we look at this, the double bond over here is between this carbon and this carbon, and we can see that this carbon here is attached to 1, 2 and 3 other carbons, and this one over here is attached to just 1 and 2. So this is our most substituted carbon, which means when this double bond breaks, okay, and one of the electrons react with this radical, the bromine will be attached to the less substituted one over here, and then the second electron over here will be what brought to this carbon, which is the most substituted one. So we have this. Okay, sorry for how I'm showing the arrow poorly over here. So we have this, and then the radical will be here, and then we have the bromine what attached to the less substituted carbon. So from here another what HBr molecule will come, and then will also react using one electron to what to give us our product. So our product will now be what this, okay, with the hydrogen over here, then plus the Br radical in solution, which will then go and react with what the starting material again to form another product for us. So thank you so much for watching. This is how we go around writing the mechanism for what the free radical addition of what hydrogen bromide to an alkane in the presence of what a peroxide, and this reaction in terms of what regiochemistry goes via what the anti-Markovnikovs addition. So thank you so much for watching once again, and I'll see you in the next video. Bye bye.